Hello everybody, this is a video which is going to talk about a Blackwell's Informativeness theorem applied to health technology assessment guidelines, which was published by Hans Keiding in 2016. So without further delay, let's go and get started. So as I previously stated, this is a video that's going to present the results from Hans Keiding's 2016 paper on the foundations of guidelines for health economic evaluation. Using the presentation from his textbook, Theoretical Health Economics. This is a great book, get it. The paper presents a version of Blackwell's Informativeness theorem, which is relevant for the use of value of information analyses and shows the broad relevance of them in informing decisions regardless of the principal decision maker's preferences. The novel result from the paper is that while guidelines can reflect the preferences of how decision makers rank cost effectiveness analyses, results from value of information analyses have broader sets of implications. Value of information analyses can be ranked with the simple rule of the following. Studies with more observations on different states of the world are better than those with less. This video won't go through any proofs. Rather, I will talk about the relevance of these results for those going and conducting systemic reviews of cost effectiveness analyses. So just as some preliminaries, just so we can understand the theorem, we're going to consider the case of a decision maker that makes a choice under uncertainty. And in this model, there's going to be many states of the world from this at S. There's going to be a set of choices that a decision maker could go and make, which is going to be a function which goes and maps our states to outcomes. And our decision maker is going to hold a set of priors about what states of the world can go be occurring. We can also say here that our decision maker is able to go and collect information in the form of signals. So they're going to go and draw information about, say, the cost effectiveness of a technology. Say they're given some study that is given to them, and they're going to update their beliefs via Bayes' rule. We're also going to need to think about the value of information. And value of information in this context is defined by the following equation. And there's a lot going on here, but this is going to be analogous to the expected value of sample information, where our first term is going to be the probability of actually observing signal J, and the expected value of our information from observing signal sigma J. So that's going to be updating that there. And we're going to subtract off the expected value without information. And again, we're going to be looking at the choices with those signals and the optimal choices without that signal. And the thing that's nice about this definition of our value of information is that we can go and collapse this into much simpler value of information concepts like the expected value of perfect information and the expected value of partial parameter information. So this need not be in a Bayesian context. So we can just use simpler notions as I've discussed in other videos on my channel. Now we need to define a partial order on our information methods, and there's many ways to go and do it, but Hans Keiding gives us the following. For information methods, which is going to be a pairing of our vector of probabilities and vector of signals, and a second one where their cardinality is going to be different from each other, so we need not have the same amount of signals in each of them. We say that our first information pairing is going to be more informative than our second information pairing, such that for each signal that we go and we see in our second information pairing, such that P as a function of a particular signal that we go and we draw from our second information pairing, sigma hat, is going to be non-zero. And there's going to be a set of numbers that we have such that we could go and reconstruct each posterior probability P hat from the set of posteriors that we have from our first set via convex combination. So in plain English, we can get the same information on the posteriors with regards to an outcome using the information we already have. So with all that, we can get into a modified version of Blackwell's Informativeness theorem that's presented in the paper. We're going to state it as follows. Let our information pairings P sigma and P hat sigma hat be information methods, and let U be a set of utility functions, A a set of actions, such that for all vectors Q in our n-dimensional real number space, there are utility functions in our set of utility functions such that if we were to go and plug A and A prime from our set of acts, and we were going to take that and put that into our utility functions, for one set of acts, we're going to go and get a number, and there's going to be another act, if we go and we plug that into our utility function, we're going to go and get a 0. With that, the following are going to be equivalent. We can say that one information pairing is more informative than another. And we can also go and say that the value of information under one information pairing is going to be greater than or equal to than the value of information that is produced under another information pairing for all u in our set of utility functions. Now, this is going to be a powerful result. And the reason why is that regardless of our decision maker's preferences, there's a way to go and talk about ranking the value of information. That's what we have in this case. Now, what this means practically is that when deciding on a ranking of information methods, such as determining which cost-effectiveness studies are more useful than others in informing a decision maker's decision in the context of, say, some systemic review, the preferences of our decision maker does not go and matter. The use of HTA guidelines are decision maker specific, and this helps them rank the cost-effectiveness of different technologies. However, guidelines surrounding the value of information analysis is going to be ineffective as there's a uniform definition on what defines more information in this context. As a rule, information methods can be ranked as follows. The studies that have more observations about different states of the world and signals that inform them are going to be more informative than those that have less. This is kind of a sunshine mantle to bro flavored theorem for HTA guidelines on value of information analysis, meaning you can say whatever you want with regards to how results should be presented, but at the end of the day, the studies that provide more information on the different states of the world and the kinds of signals that are out there are going to be better than those that provide less. So this is a really cool paper. I think it's underappreciated, and I hope you enjoyed this video, found it informative at the most, entertaining at the least. Thank you so much.